Alright, okay. In this video, I want to talk a little bit about how to calculate something called empirical and molecular formulas for compounds. And for those of you that have just watched the calculation of percent mass video, I apologize. I kind of got a little bit ahead of myself and touched on empirical and molecular formulas in that video. Perhaps I should have left that until this one, but anyway. For those of you that were watching the video and wondering what the hell is he talking about in terms of empirical and molecular formulas, well, this is what the hell I'm going to be talking about in terms of those, okay? So empirical and molecular formulas. Well, you'll have heard the term molecular formula before. It's the ratio of atoms of different elements in a molecule. For example, the molecule benzene consists of 6 carbon atoms and 6 hydrogen atoms. It doesn't tell you anything about the structure, it just tells you the formula, what atoms are present. So the molecular formula is the actual number of atoms of each element present. As for the empirical formula, this is something slightly different. The empirical formula is the lowest whole number ratio of the atoms of each element present. In other words, we take the molecular formula, or we can get to the empirical formula from the molecular formula and say, well, what number can I divide both of these through by to get the lowest numbers possible? If the numbers are the same as they are here, then the answer becomes very simple. 6 and 6 both divide through by 6, so therefore the empirical formula for benzene would be simply CH. Okay. And depending on the compound, let's say something like glucose, for example, C6H12O6. Well, once again, we just divide through by the smallest number, which in this case is 6, and we get, for an empirical formula, we get CH2O. Now, the thing to understand about the empirical formula is that CH2O is actually the empirical formula for a bunch of different molecules that all happen to have this ratio of atoms to each other. So the molecular formula is unique to every single molecule. The empirical formula actually can apply to several different molecules. Okay, so that's the difference between the two. So let's do an example. Whenever you're asked to calculate the empirical and molecular formulas, and I'm just going to shorten this to EF, and then MF for just molecular formula. Okay. So let's say, what's the empirical and molecular formula for a molecule that has this data associated with it? And whenever you have a question like this, you always have to be given something about the amounts of carbon or the amounts of the constituent elements in the molecule. Usually it's in the form of mass percent, so let's just do that. This molecule that we're talking about has 38.70 mass percent of carbon. The mass percent of hydrogen is 9.74%, and the mass percent of oxygen is 51.55%. The molecular weight of the molecule is 62.07 grams per mole. Okay, so that's the molecular weight of the thing we're trying to find the empirical and molecular formulas for. So these are the 4 things that you'll always need to be given in order for you to be able to do the necessary calculation. Alright, so that's the molecular weight. And you've got the amounts in percentages of each atom present. The question is then, what do you do with those? Well, the first thing to make sure that you can check is that all these do in fact add up to 100%, just to make sure nobody's messing with you. Now it turns out that these add up to 99.99%, which, you know, as far as we're concerned, is 100. So I can say that's essentially 100%. And then we can do something that we touched on in the last video. Because if I need to get to a formula, the only way for me to get to a formula is to go via the number of moles. Because remember, in this formula, this is a mole ratio, it's not a gram ratio or a percent ratio. So somehow I have to convert these into moles. And the easiest way to convert them into moles is to go via grams, because we saw in the last video about how we can do that. So let's just go through this and see what we can do. If my complete percent is 100 and then 38.7% of that is carbon, I can just equate all that into grams, and I can say 38.7 grams of carbon is present in my molecule, as is 9.74 grams of hydrogen, as is 51.55 grams of oxygen. Alright, crap, I didn't leave very much room here, oh well. And I know that in 1 mole of carbon I have 12.011 grams of carbon, just as I know that in 1 mole of hydrogen I have 1.008 grams of hydrogen, and in this number of grams of oxygen I have 1 mole and then 16 grams of oxygen on the bottom. Alright, so that's carbon, hydrogen, oxygen. So what we're going to do is just calculate the moles of each. So let's do that. You can see for the carbon here it's going to be slightly over 3 divided by 38.7 divided by 12.011 gives us 3.22 moles of carbon. Alright. And you can see for hydrogen the number of moles is going to be a lot higher, because although the grams is smaller, the grams here is much smaller as well. And it ends up being 9.66 moles of hydrogen. Then for the oxygen, we'll do the same thing. And what we get is this. So we have a number of moles of carbon, hydrogen, and of oxygen. So can we say then, okay, here's my formula. Well, of course we can't say that. It doesn't make any bloody sense, does it? So how are we going to get around that? Because these formulas are always made up of small whole numbers. The simplest way to do this is to take the smallest of these three numbers and just divide everything through by it. Now the smallest number here happens to be 3.22. So if we divide everything through by 3.22, we get a formula that makes a lot more sense. We got C1H3O. This is the smallest whole number ratio of our atoms to each other in this molecule. In other words, this is the empirical formula. Alright? So that's the first part of the question done. That's the empirical formula. But the question is now, how do we get to the molecular formula? Well, which part of all this information have we not used yet? Well, the only piece we haven't used is the molecular weight. And not surprisingly, the molecular weight is what we're going to use right now. So we need to see essentially how much bigger is the molecular weight than the empirical formula. And so we're going to calculate something called the empirical formula weight. So we're going to add up all the weights of here. So we're going to take the molecular weight, put it on top, divide it by the empirical formula weight that we're going to put on the bottom. Alright, so that empirical formula weight, its carbon is 12.011, 3 hydrogens is 3.024, and oxygen is 16. So this gives us 12.011 plus 3.024 is 15.035. 15, that's 31.035 grams would be, well, let's just do 31.035 grams per mole of the empirical formula. We already know what the molecular weight is. It's 62.07 grams per mole, and it shouldn't be much of a surprise to see that these two actually exist in a whole number ratio themselves. Units will cancel out, of course, and what we get is a ratio of 2. Now what that means is you've got to understand what this 2 actually means here, rather than just being the number 2, which yes, of course it is. This means that the molecular weight is twice the size of the empirical formula. Therefore, in order to get to the molecular formula, I have to multiply my empirical formula by 2. So therefore, when I do that, if I had 1 carbon in my empirical formula multiplied by 2, I get 2 carbons. 3 hydrogens in my empirical formula multiplied by 2, I get 6 hydrogens. And then oxygen, I have 1 in the empirical formula, 2 in the molecular formula. This is my molecular formula right here. And one last check. Let's just make sure that all 3 of these add up to 62.07, because they should. 2 carbons is 24.022. 6 hydrogens is 6.048. And 2 oxygens is 32. Alright. 32 plus 24, 54, 56. 0.022 plus 6 is 62.07. They add up exactly. So therefore, this is the molecular formula. That's the empirical formula. All these add up to 62.07, which matches exactly what we had here. Bingo! We have done it right. Alright, and that's how to do empirical and molecular formulas. Alright, thank you.